So when we're going to do, not confidence intervals, we're on significance tests, yes? Ladies?
Yes.
Okay. So we are going to do significance tests for mu1 minus mu2. So this is a 2 mean t-test. But your calculator doesn't tend to use the word mean. So the way you'll see it in your calculator is you'll see a 2 sample t-test.
When we say like we will use a, which we use 2 mean or 2 sample?
I would probably do 2 sample because that's what it says in your calculator, and then you know like that's the one you're looking for.
It's 4.
Okay, so again, when we're doing these significance tests, the reason that we're doing them is because we're going to take 2 samples, we're going to find the mean of each sample, and is there going to be a difference between them? Most likely, yes, right? Again, even if I took 2 samples from the exact same population and found the mean number of your mean hours of sleep last night, okay? It's from the same population, but I take 2 different samples. Is there going to be a difference in the numbers that I get?
Yes.
Yeah, it's just because of sampling variability. So what we want to do when we're doing a significance test is we want to figure out, is that difference that we got, is it really a difference, or is it just due to just random chance because of sampling variability? Right? Does that make sense? Okay. So, but in this case, we're not doing it from the same population. We're doing it from 2 separate populations. Okay? 2 separate samples, and I want to compare population 1 to population 2. Is there really a difference in those 2 populations? That's the point to this. Oh, and that's what that says right there. Significance tests help us determine if a statistic reflects an actual parameter or if it's due to chance variation. So when analyzing the difference between 2 sample means, the null hypothesis has the general form. What do you think?
X bar.
For my null hypothesis,
Mu sub 1 equals mu sub 2.
good, mu sub 1 equals mu sub 2. Or, just like in the last section, right? I could say mu 1 minus mu 2 is 0. There's no difference between them. I subtract them and I get 0 because there's no difference in between them. So that's always going to be my null hypothesis. There's no difference in between these 2 populations. So when I take their 2 means and I subtract them, I'm going to get 0. So the alternative hypothesis says the kind of difference that we expect. So we either expect one of the populations to have a higher mean than the other, or I don't know which one is higher, but I just know they're not the same. Okay? So I don't know if Mayfield students get more sleep than Westridge students, but I just don't think those 2 numbers are the same. Okay? So there's our 3 different types of alternative hypotheses we could write. And then so for our test statistic, okay, so again, remember this is that formula that's on our formula sheet and just has that generic version of it, right? So what's my test statistic going to be? What letter? For means.
X bar.
T. That's okay. T. Okay. It's always my parameter. No, sorry. My statistic minus my parameter. So now, Aoife, what's my statistic going to be? X bar. What about my X bars? What am I going to do to them? Subtract them, right? So X bar 1 minus X bar 2. That's my statistic that I have, okay? So I have 2 populations. I took 2 different samples. From each sample, I found the X bar. I found the mean. And then I subtract them to see what I get, okay? Minus our hypothesized value, which is usually like 99.99% of the time going to be what? What am I hypothesizing is the difference in their means?
0.
0, right? So this is usually going to be 0, so you just don't have to worry about it. Okay. All over the standard error of my X bar 1 minus X bar 2. And again, the calculator does all of this for you. the more familiar you are with this formula for just standardized test statistics, the better off you are in terms of other things. Okay, so we get this t value, this t star value, and then what happens? We figure out, okay, so what's the probability of getting a statistic as extreme or more extreme than what we got? Okay, and that's our p value, right? Okay, so our t star value, what we got, that's our like cutoff point. Okay, if our alternative is mu1 is greater than mu2, this area here, this would be our p value, right? This area under the curve there. Okay, so my t statistic is this. I want to know what's the probability of getting this value that's above the mean or something even bigger than that. Okay? If our alternative hypothesis is mu1 is less than mu2, then it would go the other direction, right? So then here's my p-value. And then again, if our alternative is just they're not equal to each other, we have these two tails that we have to take into consideration. Okay, so our p-value is both of those. Another thing just to mention, you have to make sure when you get your p-value from your calculator, you have to make sure you write p-value. Your calculator just writes it as p. When we do a problem, I'll remind you of that again. But it's just something to watch out for. Yes, ma'am.
Wait, because I forgot. Is it when we get that p-value for the two-sided one? It's already like given to us as the two, so we don't have to kind of
Correct. Yeah. Okay. We good? Yeah. Do you like this little cartoon?
Oh my god, it's so
I
funny.
highlight this.
So cute.
I'm casually doing one of those.
Anyways, all right. Okay, so leaking helium. Here we go. So after buying many helium balloons, only to see them deflate within a couple of days, Aaron and Jenna decide to test if helium-filled balloons deflate faster than air-filled balloons. What do you think in your experience?
Helium lasts longer.
Yeah,
I don't think so. I don't know. It's like helium balloons last a long time in my house. But anyways, to find out, they bought 60 balloons and they randomly divided them into two piles of 30. Filling the balloons in the first pile with helium, and then the balloons in the second pile just get plain old air. Then they measured the circumference of each balloon immediately after being filled, and then again 3 days later. The average decrease in circumference of the helium-filled balloons. So average decrease in circumference of helium-filled balloons was 26.5 centimeters. And the standard deviation was 19.2 centimeters. Okay? Yeah. No, can't. No, come on.
Sorry.
Are you talking about balloons?
My legs really hurt. I have to stand up.
No, you can stand. Oh, I just. Anyways, okay. The average decrease of the air-filled balloons was 2.1 centimeters, and the standard deviation was 2.79 centimeters. Do these data provide convincing evidence that helium-filled balloons deflate faster than air-filled balloons? Well, okay, look at what I highlighted.
Huge difference.
Huge difference. So, I mean, honestly, you could probably just say yes, but we're gonna go through the whole first step process to see what it's gonna look like, just because it's so much fun. Okay, I know. What a way to wake up! All right, here we go. So the first part of our 4-step process is what? State. Okay, so we will. Will we estimate? We will test. We will test at alpha equals 0.05 because they didn't give us anything, right? Significance level. Okay, so my null hypothesis is going to be what? Mu1 equals mu2. Okay? My all, do we want to use 1 and 2? I mean, we totally can.
A.
How about, can we use H and A? Because I just, you know, I get confused. Mu H and mu A. Okay, so it said, do these data provide convincing evidence that helium-filled balloons deflate faster than air-filled balloons? Well, okay, before I write my alternative, I need to say what mu H and mu A is. Where mu H is what? What is it?
Balloons.
Is it the difference? The true mean difference? True mean circumference. Just the circumference.
Of the helium balloon. Helium filled.
When do I?
After 3 days.
So maybe I could say something along the lines of where mu H is the true mean decrease in balloon, I'll say in circumference for my helium filled balloons. Yeah? Okay, so then mu A is going to be the true mean decrease in circumference for air-filled balloons. Okay, so far so good? Okay, so now, so again, you don't have to, I have a hard time figuring out what my alternative hypothesis is until I like explicitly define my variables, because sometimes I get confused. So which one is going to be bigger, mu H or mu A, or are they just going to be different? Mu H is going to be bigger, it's going to have a bigger decrease, right? Because it says, is there evidence that helium-filled balloons deflate faster, so they have, you know, a bigger decrease? Okay, so far so good, yeah? Okay. What's next? Plan. Plan. Well, we will use a what?
Two-sample t-test.
Okay, 2-sample t-test. If the conditions are met. Okay, random.
It says randomly divided them into 2 piles of 30.
Good. So I have an SRS of 30 helium balloons. Balloons. SRS of 30 air-filled balloons. You could, I can't spell. You could say what Kat said. You could say, like, randomly assigned 30 helium, 30 air. So, whatever, it's something like that. Okay, I mean, this is an experiment, so, right? So, you could have just said randomly assigned 30 balloons helium, 30 balloons air. That's probably better, honestly. Okay, independent. So again, this is an experiment. We pick some balloons and we're applying some treatment to our balloons. So, I mean, I guess I could say, assume that there's more than 600 balloons in the world, but that seems kind of like a weird thing to say, right? So, what's another way to think of independent? And I'm not sampling without replacing.